We press the run button and voila, outputs or bunch of errors appear on the screen. Compiler has always been a black box for us. So today, I am going to explain what happens when you click that run or compile button. Let's define it first. So, a compiler is a software that takes our code in a high-level programming language and translates it into machine-readable code so that it can be understood by the hardware. The translation from high-level programming language to machine code consists of a lot of steps. These are the steps in the compilation process. Technically, the compilation process ends with the generation of machine code. Steps like linking, loading, and execution belong to the broader program lifecycle. We will be using this C++ program saved in source.cpp file as reference throughout this video. This program is adding two integers a and b, storing the sum in x, and printing x using cout from iostream header. So the first step in compilation process is preprocessing. The compiler fetches all files that are included using #include in the source file, and the contents of those files are copied into the file, removing the need of #include. So after preprocessing, the code contains the implementation from iostream along with the original code. Macros defined using #define are expanded in the code and comments are removed. So currently I have my source.cpp file. If in the same directory I run g++-e source.cpp in the terminal, the -e flag tells the compiler to only preprocess the source file and output the results to the terminal without compiling it further. Let's run it in the terminal. Now this is the file after preprocessing. This is our code from which comments are removed, and the contents of iostream are now pasted in this file. cout, cin are also somewhere here. After preprocessing, the compiler scans the source code and breaks it into tokens. Tokens are the smallest unit of the program, such as keywords, identifiers, operators, and punctuations. The lexical analyzer will then break the code into these tokens from our source code. The lexical analyzer, also known as the scanner, outputs these tokens as a stream, which is passed to the next phase. We can use this command to view tokens generated for my code in source.cpp. Here we go with the command, and here are the tokens being printed in the terminal. See, here we have int and then the variable names and other tokens part of the stream. Next step in the compilation process is parsing. This step checks the syntax of the code to make sure that it follows the rules of the programming language. Parsing takes the stream of tokens produced during lexical analysis and organizes them into tree-like structure called abstract syntax tree or parse tree. So for our code, the parse tree would mostly look like this. Then comes semantic analysis. It is the phase where the compiler checks the meaning of the code. After it has passed the parsing phase, it ensures that the program is semantically correct by applying rules of the programming language, such as type checking, scope resolution, and function usage. Type checking ensures operations are performed on compatible types, like checking if a and b are integers when doing sum. Scope resolution verifies variables and functions are declared before use. For example, it checks if x exists in scope before cout. Function and return validation confirms return types match function declarations. For example, int main must return an integer. Operator validation ensures operators are used with valid operands. For example, plus sign works with integers or floats or valid types. An annotated syntax tree with additional details like types, scopes, and resolved references is passed to the next phase. After semantic analysis, the compiler translates the annotated syntax tree into an intermediate representation or IR. The IR is a simplified, low-level, platform-independent code that is easier to optimize and translate into machine code. For example, the IR might look like this in 3-address code format. 3-address code format is an intermediate representation where each instruction has at most 3 operands. Like in this example, T1 equals to A plus B has the most operands, which is 3. The IR varies by compiler. So some compilers use 3-address code, while others use representations like llvm-ir. llvm-ir is closer to assembly, but still abstract enough for portability and optimization. For x is equals to a plus b, llvm-ir might look like this. Now let's see the llvm-ir in terminal for our code using this command. This command will dump the IR in source_ir.ll file. Now let's switch to the terminal and see the intermediate representation. Here's the source_ir.ll file. We have the data in llvm-ir format, where we are loading variables and storing them in after add operation. Once the IR is generated, the compiler performs optimizations to make the code more efficient. These optimizations can improve execution speed, reduce memory usage, or minimize the size of the generated machine code. Optimization happens at the IR level to ensure platform independence. This step computes constant expressions at compile time, removes unreachable or unused code, and eliminates repeated computations of the same value. It also replaces expensive operations with cheaper ones. Optimized IR after computing constant expressions and dead code elimination in 3-address code format will look like this. Notice how concise this is as compared to the previous step. Now let's see llvm optimized IR in terminal using this command. This command will apply the auto optimization level and output the optimized llvm IR to source_op.ll. Let's switch to terminal. Here is the file with optimized IR. Notice how smaller this code is as compared to the unoptimized llvm IR in previous step. After intermediate code generation and optimization, the next step in the compilation process is assembly code generation. In this step, the IR is translated into a low-level assembly code specific to the target machine architecture. The assembly code is still human-readable, but is closely tied to the specific instructions of the CPU. To get assembly code for my current program, I will run clang-s source.cpp-o source.s in my terminal. This command will save the assembly code to source.s file. Now let's run it. And this is the output I got. Your output might differ based on the architecture of your device. Machine code is the final output of the compilation process and is composed of binary instructions that are directly executable by the computer's CPU. In contrast to assembly code, which is human-readable and tied to specific CPU architecture, machine code is in binary format, and it is the only format that the CPU can understand natively. Machine code is typically stored in object files like .o or .obj, which contain the compiled binary representation of the program. This is the output after assembly code generation step. After compiling, and generating object files like source.o. The linker takes these object files and combines them to create the final executable program. The linker also adjusts memory addresses for all the variables and functions in the object file so they can be loaded correctly into memory when the program is run. In addition, the linker may combine multiple object files and ensure that external functions or variables are properly linked to your program's code. When you compile a program without specifying an output file name, the linker generates the default executable file named a.out. To get the executable, run this command in terminal. This will generate an a.dot file in the directory. Let's run it quickly. Here is our executable a.out. But what happens if we try to open it? As you can see, it's just a bunch of gibberish. That's because a.out is a binary file. It contains machine code that the CPU understands. Once we have our a.out file, the next step is loading and execution. But what exactly happens when we run ./a.out? Let's see that in terminal. When I run the file, I see the output generated by the code, which is 15, the sum of A and B. So loader takes the final executable and loads it into the system's memory to prepare it for execution. It loads the program into appropriate memory locations, sets up stack, heap, and other memory regions needed for execution. It resolves addresses for variables, functions, and other components, and loads any dynamic library or shared objects that the program depends on. Finally, once the program is loaded into memory, the operating system hands control over to the program's entry point, usually the main function. The program starts executing the instructions in sequence beginning with main and progressing through program's logic until it terminates. During execution, if any errors are encountered, the program might crash or throw exceptions, depending on how errors are handled in the code. Once the program has completed its tasks, like printing up output, performing calculations, it exits and the process terminates. We went through all the steps involved in the compilation process and hopefully made the black box a little bit more transparent. By understanding these steps, we can better debug, optimize, and appreciate the work done behind the scenes in making our code